Oh, I didn't see you come in there. I'm Igor Anisimov, and this is my associate Nathan Willbanks, and we're chemical engineering undergraduate students at the University of Connecticut.
Hey Igor, while they're here, why don't we show them our presentation on the lithium-oxygen battery?
That's a good idea, Nathan. Our topic was based on the American Institute of Chemical Engineers article, Polymer-Based Carbons as Potential Materials for Energy Storage in Lithium-Oxygen Batteries.
In our discussion, we'll be giving a general overview of a battery structure and how it functions. We will then compare this to an alternative lithium battery, which is widely used today in cell phones, laptops, and other common electronic devices. We will then describe a newer third type of battery, the lithium-oxygen battery. We will describe the composition and function of this battery, including the function of its cathode, its highest distinguishing feature. Finally, we will explain the advantages of using this new system.
A battery provides power to an outside source called the load by passing electrons through a continuous circuit. The power is ultimately derived from these electrons. Electrons are initially gathered at the negative electrode called the anode and transferred through the circuit to the positive electrode called the cathode. The natural tendency of these electrons is to flow in the most direct course from negative to positive. To overcome this, a battery must contain a separator which is semi-permeable and will not allow the electrons to pass through it. In this way, the electrons will be able to flow through the circuit.
The lithium-ion battery is a precursor to the lithium-oxygen battery, but functions similar to a generic alkali battery. It contains the same main parts but differs in their compositions. The cathode is generally composed of magnesium dioxide. The anode is composed of lithium, and the semi-permeable membrane separating the two chambers is composed of lithium salt and an organic solvent such as propylene carbonate and dimethoxyethane.
When the battery is in use, ions of lithium move through the electrolyte from the anode to the cathode and deposit on the cathode. The electrons follow the same course along their own individual circuit. When the battery is recharged, the lithium ions move back to the anode by the application of an outside charge. The movement of lithium ions happens at a high voltage, 3.7 volts, as compared to a typical alkali battery which produces only 1.5 volts. This advantage allows for lithium-ion use in compact devices like cell phones.
The lithium-oxygen battery uses a lithium anode similar to a lithium-ion battery. However, it does not use an aqueous medium to catalyze reduction at its cathode. The cathode is instead comprised of a porous material which allows for environmental elements to become involved in the reaction. The cathode of a lithium-oxygen battery is made out of a porous carbon, a catalyst such as iron oxide, copper oxide, or cobalt oxide, and a fluoropolymer binder to enhance conductivity. Choosing the electrode porosity and the ratio of materials in the cathode can greatly alter the overall performance of the cathode. The ideal ratio of cathode composition is still being experimented on.
The key principle being described here is that the cathode is not previously packed with a specific element to be reduced, as in an ordinary battery. In this case, the element being reduced is oxygen, which can be obtained from any immediate environment. The oxygen is reduced at the cathode surface, forming an oxide ion with a positively charged lithium ion. Upon reduction of lithium, the newly formed dilithium dioxide deposits on the carbon-composited cathode. This formation of Li2O2 is the key factor that makes the battery so much better. This structure deposits on the carbon but will not intercalate, meaning that it will not form a crystal lattice, so that the whole process can be easily reversed. Carbon's tetrahedral bonding nature allows for a high porosity between molecules and high surface area to collect the Li2O2.
As Igor mentioned, the lithium-oxygen battery does not contain a solvent to perpetuate reduction as previous batteries did. Reduction is propelled by oxygen from the environment, and so the battery itself can be made smaller, more lightweight, and more energy dense. Due to this high energy density, a lithium-oxygen battery can in general store 10 to 15 times the power of a same-sized alkali battery. Since the dilithium dioxide does not form lattice structures within the carbon cathode, the battery can be reused multiple times. These advantages collectively make the lithium-oxygen battery a great candidate for future use in commercially owned electric vehicles and other green applications.
In conclusion, the lithium-oxygen battery functions in the same way as an ordinary battery, but differs slightly in its structure, reducing the oxygen from the environment. Using lithium in batteries was a step forward in technology because of its oxidative characteristics. The cathodal structure and function is what distinguishes the lithium-oxygen battery from an ordinary lithium battery. Being able to obtain oxygen from the environment will allow for more lightweight and compact energy sources in the future.
And here's a list of the sources we used in our project.
Thank you for watching our presentation on the lithium-oxygen battery. Do you have any questions?